Hello ChemComm. In Unit 11 we've been talking about solutions. Some of the most common solutions are acids and bases, which we're going to cover today. Let's get started. Let's begin by going over some common characteristics of acids. Acids are identified as substances that produce H+ ions when in solution. This H+ ion will combine with a water molecule and it'll become a hydronium ion, which is H3O+, with a +1 charge. Acids have low pHs from 0 to 7. They taste sour and they feel like water. Litmus paper and phenolphthaleins are indicators that tell us if we have an acid or a base. If the litmus paper turns red in the substance, that means the substance is acidic. And if phenolphthalein stays colorless, that also means that it's an acid. If you mix an acid with a base, that will neutralize the acid and it'll produce a salt with water. And as we said earlier, acids always produce an H+ ion when they're put in water. So you could have a monoprotic acid, which only has one hydrogen as the cation, as we can see here in hydrochloric. Or we could have diprotic acids, which have two hydrogen ions, because it's bonded to an anion with a -2 charge. And you can also have acids that have three H+ cations in that position. Common acids are hydrochloric, nitric, and sulfuric acid, which are shown here down at the bottom. Bases produce OH- ions when they're in solution. Typically they have pHs between 7 and 14. They taste bitter and they feel slippery like soap, because most soaps are bases. They turn litmus paper blue and phenolphthalein pink, and typically if you put them with an acid, they will neutralize and produce a salt. Common bases are sodium hydroxide, which is probably the most common one that we use in lab, potassium hydroxide, magnesium hydroxide, and even baking soda would be considered bases. Most cleaners that you use in your house would be considered basic. An antacid that you would take for an upset stomach would be calcium hydroxide, and that would be used to neutralize some of the acid in your stomach. So if an acid produces H+ ions and a base produces OH- ions, then what would water be? Water, H2O or HOH, would have a pH that is neutral or 7 because it's in between an acid and a base. It has the ability to produce both of those ions. What you have here is equations showing the dissociation of the different acids when you put them in water. So hydrochloric acid is going to break apart into H+ and Cl. This H+ right here is what makes this an acid. It's producing an H+ ion. Where KOH and LiOH, they're going to break apart into their cation and anion, and their anions are OH. This is what makes this a base. Anytime you see an ionic compound with an H+ cation, that's an acid. OH anion, that's a base. The next thing we're going to talk about is the difference between strong acids and weak acids, and strong bases and weak bases. When we say strong and weak, we're not talking about how concentrated the acid is. What we're really talking about is how well that acid dissociates. Remember, an acid in water will dissociate, producing that H+ ion. So strong and weak are terms that tell us how well that it does that. So a strong acid dissociates 100% into ions, where a weak acid will only partially dissociate, only maybe 15% of those ions. There's a list of strong acids here on this slide, HCl, HBr, and so on. And you can see they dissociate into a hydrogen ion and whatever anion they're paired with. Weak acids, though, like acetic acid, which is vinegar, or oxalic acid, they will not dissociate completely. We still write the equation the same way. We just know that they're weak acids, and so when put in water, all of those ions won't dissociate from each other. Bases have the same categories. A strong base will dissociate 100% of the time. There's a list here of 8 strong bases, and we can write the equations for those. There are also weak bases that dissociate less than 15% of the time. Ammonia is an example of this, which is a household cleaner, and ammonium hydroxide is another example of this. As you can see, the equation for the dissociation of water is what happens is the ammonia is taking a hydrogen from water, which leaves us an OH- ion. A lot of times when we put weak acids and weak bases in water, we get reversible reactions. And so we said it only dissociates less than 15% of the time. What's happening is some molecules are disassociating and others are coming back together. And it's kind of this forward and backward movement that gives us these weak acids and weak bases. Strong acids and strong bases don't do this because they dissociate 100%. Typically, the way we represent this is by showing a reversible symbol when we show the dissociation. So what we're saying with a weak acid here is not only is there this forward direction reaction, there's also this reaction of these two ions coming back together. And that's why you only get partial dissociation. Same thing happens with weak bases. But notice with a strong acid and strong base, we only get an arrow in one direction because they dissociate 100% of the time. Neutralization is when we mix an acid and a base together. What this is going to produce is an H plus ion and an OH ion are going to bond together and produce water. And then the other two cations and anions are going to pair together and form a salt. It's not necessarily the salt you think of, like table salt. Any metal cation and non-metal anion coming together is what we would classify as a salt in chemistry. So neutral solutions are always going to have the same amount of hydronium and hydroxide ions. Another concept you should be familiar with is don't think of acidic and basic solutions as one or the other. Acidic solutions simply just have more H plus than OH negative ions. It doesn't mean it's all or none. The same thing with basic solutions. They have more OH negative ions than H plus ions. So the more acidic something is, the more H plus ions it has, and the more basic something is, the more OH negative ions it has. So you can see here to the left, this would be a very low pH. We only have one OH negative ion, but mostly H plus. And this one would be very high pH or very basic because we have lots of OH negative ions and very few H plus. Let's take a few minutes to talk about the pH scale. The pH scale really tells us the concentration of H plus or OH negative ions that you have. pH stands for power of hydronium ion. It's telling you to what power of 10 do you have of H plus ions. It's really a molar concentration. The closer to the power is to 0, the more likely that that's an acid. 10 to the 0 power would be a very acidic solution, where 10 to the 14th power would be a very basic solution. You can also do the scale with OH negative being the focus. We call this pOH, and it measures alkalinity or how basic something is. And the scale would be opposite. So if a substance had a pH of 1, then it would have a pOH of 13 because it would be opposite. You can kind of see this here on the scale. We see something with 10 to the 0 here, which a pH of 0, it has a pOH of 14. And as you can see, they overlap in the middle. So if there's a pH of 7, the pOH is also 7. This chart just kind of shows you some of those things we were talking about. We see that milk has a pH of 6. That means it has a pOH of 8. And therefore it's acidic because the pH is lower than 7. Stomach fluid, pH of 1, that means the pH of 13, and it's acidic. Basically, you can work your way the rest of the way down, but you can see that if we add up the pH and pOH, every time that's going to add up to 14. So if you're ever trying to figure out what the pH or pOH is based on the other, make sure that the pH and the pOH add up to 14. Let's take a few minutes to apply acids and bases to some things we see in our natural world. Often, lakes and rivers aren't affected by acidic rain very much. Why is this? Most of the time, lakes and rivers have things called buffers or substances that are capable of neutralizing acids and bases within them. We have natural buffers in blood or your stomach fluid, and this helps things from getting too acidic or too basic. The way that a buffer works is that it bonds to some of the ions that is produced by an acid or base. And so when you introduce an acid into it, it doesn't change its pH very far. Here's some hydrochloric acid. When we add that to the solution, we would expect to get a lot of H plus ions. But since there's already a buffer dissolved into it, some of those H plus ions are bonding to these negative ions, these HCO3 negative ions. That's using up some of those H plus ions, and therefore there's only one free H plus ion present, and the buffer keeps that substance from changing the pH too much. The last thing we're going to talk about here is the difference between strength and concentration. We've already talked about strength. A strong acid or a strong base is based on how much a substance disassociates in water. A weak acid does not. But the danger in an acid and a base comes from concentration. It's a measure of how many particles are dissolved in that solution. So you can have a strong acid that is dissolved into a solution, but you can make it very weak because you just don't have a high concentration of particles. Or you can have a weak acid that's very concentrated and it can be very dangerous, even though it's dissociating a little bit. Is it possible to have a strong acid that is dilute? Absolutely. Is it possible to have a weak acid that is concentrated? Absolutely. We can give you representations of this. This is a concentrated weak acid. It's an acid that doesn't dissociate all the time, but it's very congested because it's very concentrated. Here's a concentrated strong acid. Notice it disassociates completely. Everything is disassociated into cations and anions, and it's very dense. Dilute weak acid. We only see one of these dissociate, where this is a dilute strong acid. We have complete dissociation, but it's not very concentrated. Remember, when it comes to acids and bases, how concentrated they are will make them more dangerous. It's not necessarily if it's a strong acid or a weak acid. Hopefully you have a better understanding of acids and bases now that we've walked through that. Make sure you do the activity today. We'll see you soon.